It's my pleasure to introduce our speaker, Professor Izao from the Technion. Izao has a bunch of interesting connections to Michigan. He's the academic grandchild of Dan Kodacek, who was a professor in this department in EECS for 10 years. And he has also been my co-PI in a large grant from the Khan Foundation, a $15 million autonomous systems mega project that ended a couple of years ago and has funded a lot of work here in Michigan and in Israeli institutions as well. Zal?
So the title of the talk is Nonlinear Mechanics and Dynamics and Control of Under-Actuated Robot Motion. So now we're talking science. I want to apologize that this is not going to be a standard seminar in control theory. I come from mechanical engineering and I come from robotics. So robotics, of course, is an interdisciplinary field that has, of course, aspects of computer science, if you will, so computation, machine learning, AI, SLAM, localization, signal processing, image processing, path planning, algorithms. But I come from the mechanical engineering, so my contribution is to think of a robot as a mechanical system that generates motion, applies forces applied on it, some actuation, and of course, it has to move. There is some motion, so obviously we have a dynamical system. Since we have actuation, we have inputs and outputs. It is a control system with or without feedback. Often the dynamic is nonlinear, sometimes involve constraints. I will talk a little bit about non-autonomic constraints, which are actually very important part. Focusing on under-actuated systems in which the number of degrees of freedom is smaller than the number of actuated inputs is smaller than the number of degrees of freedom. And this means that we have some passive degrees of freedom, non-actuated degrees of freedom, which evolve passively by mechanical effects like elasticity, inertia, friction forces, contact transitions, and many more. And here is the overview of my research philosophy or my research principle. I try to start with simple mathematical model. If they are not simple enough, I try to simplify them, try to find the simplest one. If they are complicated, I give them to Shai. If they are too complicated, if they are very complicated, I give them to Inigo, complex systems. So I try to go with simple models of under-actuated robot motion and analyze the dynamics, apply analytical tools, the dynamics, the mechanics, the control, try to find the influence of the dominant parameters, try to do optimization of performance. You will see sometimes there is stability issues, try to think of conditions for stabilization. And then we go to the lab and design robots, assemble the robots, fabricate the robot, and conduct experiments, simple experiments, as simple as possible, and then take the measurements and analyze the results, compare with the theoretical predictions, and make observations and conclusions. And then probably we find that some assumptions of the models are overly simplifying and we have some discrepancies, and then we need to improve the model, make it a little bit more complex, more rich, or it has more rich dynamics, other effects. And then we repeat the process. We can optimize the new model, try to find optimal performance and stability conclusions, and then go to the experiment, maybe design another set of experiments, maybe design a different robot, and then do it in a cyclic manner in a way that we use the mathematical analysis as a way to optimize the performance or better understand the robot, and use the robot experiments in order to improve the models, to improve fidelity of the models. So during this joyful process, I try to draw inspiration from biology, from biological locomotion, and also from cute moving toys. This is the outline of the talk. So I have 3 parts. I'm not sure I will be able to cover 3 of them in the same level of details. Maybe at the 3rd part, I will have to quit or go faster. But let's see how time moves and how much you want to go home for the weekend. So we start with the first part, which is locomotion of under-actuated robots with passive wheels. And beginning with a very simple model, the 3-wheel snake. inspired by biology, by a crawling snake, which is doing something undulatory, something traveling way. And this is the robot, three links supported by wheels, and they are connected by joints. On the joints, we have servo motors. This is the planar model sketch of this. We have generalized coordinates, Q, the vector of coordinates. We have x, y, theta, position and orientation of the central base, the central link, and phi1, phi2 are the two relative angles at the joints, which we assume they are prescribed or controlled by the servo motors. The system has constraints. In a simplified manner, we assume that each wheel is free to roll on a tangent direction, but it's not allowed to skid, to move, to slip in the lateral direction. And this imposes constraints which are linear in the vector of generalized velocities, q dot, and non-linear in configuration. So it's a matrix W times q dot equals 0 vector. In geometric mechanics, there is a concept of dividing the coordinates into body variables and shape variables. So the body variables are x, y, theta, position and orientation of the moving base. And the shape variables are internal shape, that's phi1 and phi2. And here we simply assume that they are actuated as a periodic sine wave with amplitude, frequency, and phase shift, just like this sinusoidal motion you can see in the movie. And then you can look on this equation here, W, you can actually decompose it into constraints and submatrices, WB, WS, and a relation between the body velocities QB dot and shape velocities QS dot. And this WB is a square matrix. It can be inverted. And then we obtain a relation between the shape velocities and the body velocities, which is actually a first order ODE system. Since we regard the shape variables as inputs, we have a driftless nonlinear control system. It's also called kinematic system because it is time invariant, which means that if we have some trajectory that we take in the space of the shapes, we can scale the time and we will follow exactly the same resulting trajectory in the body, but with the same scale time. So it's invariant to time scaling. For example, if I multiply the frequency by factor 3, I will have the same result by just velocity is speeded up factor 3. So in geometric mechanics, people who know how to do it, like Shai and Ross Hutton and many more, they can do Tony Bloch. So they can do evaluate these gates, the trajectories, and find what is the net displacement. There are many nice methods that I don't have time to talk about today. We also have the dynamic equations, mechanical equations, Lagrange equation with constraints if you want. And one can use them if you want, for example, for a given motion, you want to know what are the constraint forces, this capital lambda here, and what is the actuation torque vector at the joints. So we don't really need them. In this case, it's first order system, but we can use these equations to find forcing. But there is a problem with this model. It fails. It actually doesn't always work because we need to do inversion of this matrix here, WB. I think the laser pointer is weak. This. And it turns out that this matrix becomes singular at some configurations, and among them also the condition that phi1 equals phi2. So everything which is symmetric, like this, like straight line, maybe I should hold the sign, okay? So any symmetric configuration, if you cross it, there is singularity and you can't invert the matrix, which means that if we evaluate the body velocities or constraint forces or actuating torques, they have unbounded divergence to infinite magnitude. And this is, of course, unphysical. There is no, maybe there is velocity jump, but definitely the actuators, they have saturation. And the constraint forces, they come from reaction forces, tangent reaction forces, so they are limited by friction. So obviously something cannot hold here. And what cannot hold, actually our assumptions cannot hold. The non-holonomic constraints become linearly dependent, that's singularity. And this means that the no-skid constraints cannot hold. And if we take the robot from the lab and take measurements and measure the skid velocities, which are supposed to be 0, they are not 0. They're actually completely non-negligible, very significant. which means that we need to improve the model. We need to take back and relax the assumption of no skid and assume there is possible skidding and friction forces, which are according to some friction law. So one way we did it was Coulomb friction. How many of you are mechanical engineering? Okay, so Coulomb friction supposed to be familiar? Okay, so Coulomb friction, the problem with, I don't go into the details, maybe more physical, but the problem with this is that it's non-smooth equations. So it's hard to integrate and definitely hard to analyze. So if we want a simpler model, we want to be lazy, a better solution is smooth dynamics with viscous skidding, with viscous friction, which means that the force in the transverse in the lateral direction is linearly proportional to the skidding velocity with a coefficient. And we also add rolling dissipation because this is also a physical phenomenon. So there is another damping coefficient in the rolling direction for each wheel. Very easy to integrate this into Lagrange equation. You formulate the Rayleigh dissipation function. If you study Lagrange equations, if not, just Google this term, Rayleigh dissipation, and you have it, and you can integrate it into the equations. The problem is now we don't have the first order equations, we have the second order equations, the mechanical equations. So the time invariance, the nice property of time scaling is lost. And if I'm doing some input, some sinusoidal input for the joints and changing the frequency, the result will not scale in time. It will change non-monotonically. So the actual displacement per cycle is changing with the frequency, and we have an optimum. These are from experiments. And the theory supports this. You need, of course, to calibrate the damping coefficients to fit them to the data. But in principle, we have it in experiments too, in the simulations too. So this is the kinematic snake with two actuators, one for each joint. There is another interesting configuration which we call semi-passive. Semi-passive means that one joint is actuated with a servo motor, but the other one is with the symmetric mechanism of spring. So easy to simplify this by a torsion spring with linear stiffness, torsional stiffness. And also we need to add some dissipation, some damping, because the springs are never ideal. They're never fully conservative. And once we do this, we can also study, for example, what is the effect of sweeping frequencies. And again, we have an optimal frequency which maximizes the velocity or the displacement per cycle. And here we can take various versions. We can take it with rolling dissipation, without rolling, with skid dissipation, or we can even leave the non-autonomic constraints. And the interesting thing is that it can cross singularities while maintaining bounded forces. Very interesting. The dynamic enforces this, but I don't have time to prove or to detail too much about this. So this is the three-wheel snake, but this is not the simplest possible toy that I can think of because it has 3 links and 2 joints. Think about something with 2 links and 1 joint. Here it is. This is the twist car toy. That's a name. It had an older name, Roller Racer, basically the same toy, but 30 years ago. The kid is riding on this toy. No need to push with the feet against the ground. No need to lean sideways. No need to go only downhill. You can go on level flat plane, horizontal plane. All you need is to oscillate the steering handlebar. And the robot demonstrates that there is this caster, there is this distance between the steering axis and the wheels. And this is actually generating some lever that pushes. So this thing moves. So then we go to a model. Model, again, 2 links and 1 actuated joint. No skid constraints. We begin with no skid, assuming no skidding. So we have non-autonomic constraints. The input is sinusoidal with frequency and amplitude and some mean value. The mean value, phi naught, according to the notation here, phi naught equals 0, phi naught equals pi is just like the twist car. When the 2 links are folded one on top of the other or one under the other. Phi naught equals 0, it's when it's open, straightened configuration. And for some reason, the toy roller racer is similar to twist car, phi naught equals pi. But in the analysis, in all the papers about roller racer, for some reason, they analyze this stretch configuration, and it turns out that this one is more interesting. So most of the time we also analyze this. It's basically not really big difference. The thing with the no skid constraints is that now we have only two wheels. So this WB is not a square matrix, it's 2 by 3. So we need more information, and the information comes from the dynamics. So we need some scalar momentum equation in order to complete the dynamics. It's not a kinematic system. It's not time invariant. One more thing that we did, which was not present in previous works, was to use the rolling resistance, because if we don't use any sort of this kind of dissipation, we have something unphysical, that the forward velocity is actually oscillating but diverging to infinity, like accelerating unboundedly, and also the orientation angle is oscillating with diverging amplitude, which is not physical and not observed in experiments. So it's very good to add this dissipation, and then we get convergence to periodic bounded motion. Okay, the next thing is that we did some analysis, some simplification. So we assumed small amplitude of the oscillation, call it epsilon, and then we do perturbation expansion. Familiar to you guys? It's like Taylor series, but you take extra, it's like linearization, but you take also the higher order terms, and then you sequentially solve for each order of epsilon, all the state variables of the dynamics. And specifically, we're interested in the forward speed. So the forward speed is a power series in epsilon. And in the steady state solution, the governing term is actually quadratic. It's multiplied epsilon squared times V2. And what is this V2? This, after some scaling, the non-dimensional order 2 solution looks like this. It has a constant, then it has a transient decaying term, and then it has periodic term which is oscillating in double the frequency of the input. And we're interested in this constant. The constant is actually the mean speed. And here is the expression. We have an explicit expression for the mean speed as a function of parameters. Everything here is non-dimensional. So all these alpha, kappa, beta 2, eta 2, everything here is actually some ratios of link lengths, center of mass position versus length, mass ratio, moment of inertia ratio. Everything is non-dimensionalized. And you can see the influence of each parameter. Specifically, if you look on the influence of omega, it's just monotonic, it's quadratic. So there is a scaling. If I multiply omega by 2, my mean speed in steady state would be factored by factor 4. So it's really monotonic, but with the other parameters, it turns out that this is not necessarily monotonic. And we can find combinations of physical parameter values that actually give this mean speed to be positive or negative. So we can actually make reversal in the direction of motion depending on parameters, and specifically, we can shift position of the center of mass. For example, the rider is shifting a little bit forward or backward. So the theory predicted, for our surprise in the first time, that we can reverse the direction of motion by just shifting the center of mass. And we did it in experiment without a rider, but this here is something which is like a rider. Okay, so this massive rectangular block, black block here, can be removed, and when it's removed, the center of mass is shifted. The parameter values were designed such that removing the block will reverse the direction of motion. You can see now, beautiful shoes, okay. Okay, so this was working, but if you can see a lot of skid. Can you see that the smaller, the wheels of the smaller link are actually skidding a lot? So the no skid assumption is not really realistic. And what does this mean? For us, it's like another homework. So we need to go to the model and add skidding. Actually, we see it in the experiment. We see non-negligible skidding. And we should add, again, so we do the same trick. We have viscous friction in skid direction and in roll direction, two different damping coefficients. And once we do that, we can go back to do the asymptotic analysis. It becomes a little bit more ugly. The structure here is the same, but the expressions inside are more complicated. The D1 is now the mean speed. all these A and B coefficients are very long and very complicated dependence on parameters. But more interestingly, the dependence on omega, on the frequency, it's no longer monotonic. We have omega squared, but then it's multiplied by a rational function, polynomial over polynomial of omega. And this is interesting, and more importantly, this is non-monotonic. And we found some physical values, realistic physical values, in which, again, we can reverse the sign or the direction of the motion by changing the frequency. Okay, so for low frequencies, we can have positive mean speed, and for high frequency, we have negative mean speed. And let's do some experiments. So waving very slowly, low frequencies. It is moving slightly to the left, very slowly, because most of the motion is absorbed by the dissipation, by the friction. Now let's try to wave with higher frequency. It takes time to reverse, but then it moves to the right? Okay? But this is not right. This is actually the opposite direction. If I'm comparing now, again, the theory says that for low frequencies, I have positive speed. For high frequencies, I have negative speed. But there is a notation, there is convention of notation. What is negative and what is positive? Positive is in the direction of the small link. That's our convention. And the experiment was just the other way around. For low frequencies, it was negative. What went wrong? Something was wrong in the model. Any suggestion? What should we improve? Anyone speaking French? French scientist already mentioned. Charles Augustin, I think. That's the first names? Coulomb friction. Okay. Think of electric charge. Okay. Coulomb law is okay for you. Okay. So try to do Coulomb friction, or at least a simplified version of Coulomb friction, in which the lateral force is minus the sign of the lateral skid velocity times a constant. So it's piecewise constant, just sign dependent. And when we do this and do it in simulations, it's a little bit tricky to do the numerics, but we get the right sense, at least, of the direction reversal. But we have a lot of other large discrepancies. If you compare really time series, one to one, you will see a lot of discrepancies. It's not really working perfectly. All these are results from this summer. Actually, this graph I received of these simulations I received only 2 days ago from my student, wonderful student. And the intermediate conclusion is that friction models are very significant and crucial, but it's difficult to find them, to identify them from experiments, and difficult to analyze them numerically and analytically. Another toy, maybe more fascinating toy. You know the waveboard? Anyone here knows how to ride a waveboard? So the rider has to do something like this, twisting the hip with its own inertia, which is larger than the board itself. And the wheels are free, but they also have axles. They have axles like this. So a planar model of this would probably be something like this. Here is the wheel, and there is a lever again, just like a twist car. And this is the rotor. Why we have torsion springs, maybe later, I don't have time to explain now. But this was too complicated, so we can do numerics, but asymptotics was too complicated. So we chose to use a simpler model, which is kind of a variant of the twist car. We call it RAPS twist car, rotor actuated passive steering twist car, which means that it's the twist car, but now the steering angle is passive. There is no rider touching the steering wheel. And this is evolving passively, and the actuation is this hip joint, which is actually a rotor, which is reciprocating in some frequency and amplitude. For simplicity, we begin with no skid constraints and add some dissipation, viscous rolling resistance. Also for simplicity, we assume that all the masses are negligible except for the rotor, because the rotor is our human, and the rest is just piece of wood and wheels. And so it's better to simplify. Then some simulations. For some actuation frequency, here is the result of the passive joint angle. You see there is a transient, and then it converges in steady state to periodic oscillations about 0. which means symmetric oscillation about here 0 is actually the folded configuration. So it's just like that whisker is moving, but this happens passively because of the rotor. And of course, this means that the vehicle will move forward. And you can see that's the speed, the forward speed in body frame. It is converging to oscillations in double the frequency of the input as expected. And then we did some asymptotics. Again, we assume some small amplitude and we do perturbation expansion and we get, this is the expression for the mean speed, the quadratic term, that's the leading term. And we actually find that there is an optimal placement for the center of mass or the center of the rotor, which gives the maximal speed. Delta is just scaled the distance of the center of mass. So this is interesting, but this is not the end. What happens if we take other frequency? Let's take a lower frequency. And now what we get is that the steering angle phi is converging in steady state to periodic oscillations, but about a non-zero angle, which means something like this, which means that the vehicle will move in circle. In average, it will move along a circular arc. And what about the symmetric oscillation? It's not that this motion disappeared, it still exists. There is a valid solution for the system, which is periodic oscillations about 0, but it becomes unstable, which means any small perturbation will cause divergence of this solution, including numerical error, accumulating error in the integration. So it's hard to see it for long times in the integration, definitely with the initial perturbation. What happens? Okay, this was one frequency, this was a lower frequency. What happens if we take an intermediate frequency in between? Now we get multi-stability. So we have a stable solution of oscillations about mean 0. We have the red one is stable asymmetric solution of oscillating about some non-zero angle. And we have some intermediate solution, which is asymmetric and unstable. So now we see that the parameter omega, the frequency, is actually affecting existence and stability of periodic solutions. So it is a bifurcation parameter. Anybody knows bifurcation? Here is the bifurcation chart for this. So omega is the scaled frequency now, dimensionless, and phi bar is the mean value of the steering angle along steady state periodic solution. So phi bar equals 0, that's the symmetric solution of motion in a straight line on average. And the solid curve, the solid line is when it is stable, the dashed line is when it is unstable. And the colored ones, the red and blue, are actually non-zero mean value. These are the asymmetric solutions in which the vehicle goes in a circular arc. And now you can see that in some regions we have this multi-stability. This is stable, this is stable. In some regions, only asymmetric is stable. And in some ranges, here we have, this is called the fold bifurcation. And what's the name of this bifurcation? It looks like a fork, right? Pitchfork. Subcritical or supercritical? Think about it. Okay, and beyond that point to the right, there is only one solution, only the symmetric solution. And if you think that the bifurcation are occurring only for changing frequency, no. You can fix the frequency and change delta, the center of mass position, and you have bifurcations also with respect to that parameter for constant frequency, which means that these are two very significant governing parameters of this beautiful nonlinear system. And they govern, for example, the stability or instability of the symmetric solution, the one which is oscillating about 0. And in the plane of omega versus delta, we can plot the regions of stability and instability of this symmetric solution. And the red curve is the stability transition curve. Here it was calculated numerically. And if we want to approximate it asymptotically, we need to do a lot of hard work. It's a paper which is right now in archive. It's not yet accepted, it's minor revision. We need to do harmonic balance and finding the bifurcation condition. We get a very complicated polynomial system. And then we need an extra assumption of another scaling parameter, which we assume to be very small. Do I need to worry about people wearing face masks? I'm joking. Okay, so after a long work and a lot of neglections and simplifications, we obtain this biquartic polynomial in omega, which is a nice approximation of the stability transition curve. How about experiments for this? These are in very preliminary stage. They are not very nice, but I still wanted to show you that not everything is nice at the first shot. So the rotor is not having sufficient inertia, so it's not really traveling anywhere. But when the student is trying to fold it, to put it in phi equals 0, it is repelled. And looks like it converges to something asymmetric. By the way, also phi equals pi is also a periodic solution, an unstable one. You see, it's repelled from this. Can you tell me on the graph, in which region are we? In which region are we on the graph? Are we in small delta, medium delta, large delta? From this stupid movie. Anyone? You have 33%, you can guess. So the symmetric solution is repelled, it's unstable, and the asymmetric solution looks like stable, so I would guess we are between this and this on the left side. Okay? Okay. Let's move to dynamics of micro swimmers. How is my timing? Ooh, I think I will have to skip the soft robotics. Okay, micro swimmers. We start with Purcell swimmer. Who knows Purcell swimmer? Literature, very famous, but for those who are with microorganisms or locomotion. So it's it's a simple model of swimming organisms, microorganisms like sperm cells. So it's again, 3 links connected by joints, no wheels at all, okay? And the actuated inputs are the 2 relative angles, phi1 and phi2, which are moving periodically. In the original paper from 1977, it was like this square loop in the plane of phi1, phi2, which is something right, left, something like this. Again, body coordinates, shape coordinates, but to formulate the dynamics, it took 25 years after Purcell. The paper by Becker was using some assumptions of Stokes flow, which means that for each moving rigid body, the forces are linear in the velocities, resistance drag forces. And for slender links, there is a proportionality between the resistance coefficient in the direction normal to the elongated link and the direction tangent to the axis of the link. And in infinitely slender bodies, this factor is 2. There is anisotropy between resistance in different directions. That's actually the driver of the motion. So another assumption is that we neglect inertia. It's low Reynolds number. If you're a mechanical engineer, you know Reynolds number, right? Okay. So we neglect inertia. We have quasi-static motion, which means that the zero sum of forces and torques on the swimmer must be 0. Since forces and torques are linear in velocities, this gives a linear relation between velocities, shape velocities, and body velocities, just like the non-holonomic constraints, but they come from a different physical origin. There is no skates, no skid. It's something from forces. And this gives a driftless nonlinear control system relating the shape variable velocity to the body variable velocity. Again, kinematic time invariant system, different physics. When applying periodic inputs like the square, and what is the circle? The circle means that phi1 is epsilon cosine omega t, phi2 is epsilon sine omega t, like this phase shift between them, something more continuous. And then you try to contract or expand this trajectory, just change the amplitude, not necessarily epsilon small. And you measure the net displacement per cycle. Again, you don't care about omega because of time invariance. And what you get is that there is an optimal amplitude, stroke amplitude that maximizes the displacement. If you increase further, there is a reversal in the direction, theoretically. If you increase it even further, there is an optimum for swimming in the other side, and so on and so forth. But this is rather large. It's more than 3 radians. It's like pi. So if your swimmer, Purcell swimmer, is capable of folding like this, like pi, then it's fine. But most of the time, it's not really practical when you build the robot. Then we did perturbation expansion, and we were able to take these numerical results and make something analytic. And I'm skipping a little bit because of time constraints. And we built several versions of this robot. The first one was tethered, and we did comparison. It was not micro. I don't know how to build microorganism or micro robot. When I have micro robot, I collaborate. I do it with experts in nanorobotics. So in order to have low Reynolds number, I had to increase viscosity. So we took silicone oil, which has viscosity 60,000 centistokes. For reference, what is the viscosity of water in centistokes? Open the book, or open Google, or raise a finger. It's one centistokes, okay? So it's very, very viscous fluid. Reynolds number was pretty small. We moved slowly, probably the movie is accelerated. And then we did this experiment of taking the sine and cosine, the circular gate, and changing the amplitude and measuring, that's the blue circle, measuring the displacement per cycle. And that was the first time that we found the optimum, which we were happy with, but we were not happy with the big discrepancy between the blue and the red. The red is simulation results for Purcell Swimmer. But it's clear why it's not working. Purcell Swimmer was designed for slender links, like very thin rods. And that's it. But the robot, if I'm going one slide back, the robot, first of all, there is this huge flotation foam, which is like extra drag on the central link, big extra drag. And also the links are not really like wires, thin wires, they're plates, rectangular plates. And rectangular plates, they behave differently. So we wanted to improve the model to reflect the fact that the robot is not really slender links. So here is a modification of the model. So we did the lazy solution. Add a sphere, because sphere is very easy to do the viscous drag coefficients, ignoring all the interaction between different links. And also we changed the ratio factor 2 between the normal to tangential drag coefficients, and we allowed it to be larger, and then we did parameter fitting. When we do parameter fitting, this is the values we get, and this is the curve, the orange curve that we get, which matches very well with the experiment. But then we were greedy. We were still unhappy because we weren't able to do to show reversal, directional reversal. So some years passed and we built another robot. Now it was untethered, and these results are really from the recent months. So the trick was, why to force ourselves to use just circle, sine and cosine, or sine with phase shift of half pi? We can do this. Sine and sine with a phase shift of psi. We can change this right in the plane of the angles, it generates a skewed ellipse. And by changing this psi phase, we actually change the aspect ratio of this skewed ellipse. We can make it fat, we can make it thin, we can make it short or tall. And with this, we were able to choose 2.7, which is phase shift of 150 degrees approximately. And with this, the blue ones are just measurements, and this is 0. And we were able to find reversal in the direction. The dash is just no, it's just a fitting, some polynomial fitting, but we were able to find the reversal. Okay, we were very happy. By the way, how did we know to take this particular phase and this particular aspect ratio? Why not 90 degrees to the other side? The answer is not in the slides. It's actually some geometric mechanics. If you're familiar with, we evaluated the height maps of Ross-Hutton for optimized coordinates. And from this, we can actually tell what should we do in order to get a reversal in direction in small amplitudes, because we had the limitation on the amplitude. This happens here in less than 50 degrees. Our amplitude was limited like 100 and something, 20, 30, 40. Okay. Things that I will not include today, optimal control. What can we do if we want to optimize even better, to consider gates or trajectories in the shape space, which are not necessarily sine waves? Can we do better in terms of displacement, in terms of energy expenditure? For this, we did the optimal control, Pontryagin maximum principle. Is this familiar to graduate students, maybe? Okay. And also using the geometric methods of Ross-Hutton. So for displacement, at least we were able to do it. Sorry, I know it's control seminar, but I have to put it in parentheses. The thing is that, again, Purcell Swimmer, all this is kinematic system. What happens if we have semi-passive? It's more realistic because we have some structural elasticity in any organism with waving a tail. It's not controlling its own shape. So the simplest way to do it is, again, semi-passive, one torsion spring, passive joint, and one actuated joint, which can be actuated kinematically. Later, we also did with torques, but this is another story. I'm skipping because we did basically the same story. We were able to show that there is an optimal, analytically, that there is an optimal frequency maximizing the displacement per cycle. So like there is like a resonance-like phenomena, the best frequency that excites the swimmer to the best. Best is our definition. It could be energy efficiency, it could be displacement. I had more slides, but I had to cut them out because of timing. So when we talk about real engineered micro swimmers, nobody really built per cell swimmers, something with motors at the joints, because it's too complicated. It's easy to build like torsion springs, something elastic, but it's very hard to build these motors unless you have a bacterium. But people were doing actuation by magnetic field, time varying magnetic field. And the pioneers in this is 20 years ago, Dreyfus, Howard Stone, Nature paper about this swimmer. The tail here is made of super paramagnetic beads connected in chain by these DNA elastic links. This sphere is a red blood cell. It's the cargo, it's not the head. And the magnetic field is oscillating like this. It has a constant component in X direction and oscillating component in the Y direction. So the direction is doing something like this, the magnetic field. And the swimmer follows this and moves in the X direction. Okay. They were able to show experimentally and also analytically, numerically, that there is optimal frequency that maximizes the scale speed with constant beta, with constant amplitude of the magnetic field. And then they did something else. They fixed the frequency and started to change the amplitude in experiments and in their simulations. And they argued something very interesting, that above some critical value of this beta, the amplitude ratio between the constant X component and the oscillating Y component of the magnetic field, beyond some critical value, there is a change in the motion, a complete change. The swimmer is actually flipping in 90 degrees and starts to move in the Y direction instead of X direction. They also argued that this critical amplitude ratio was square root of 2, and that this happens regardless of frequency, independent of the frequency. It's not that they didn't do analysis. The analysis was partial, so it was left kind of as an open question, and I will get back to this in one or two slides. So remember this question: why it's moving in Y direction? Keep X. That's the magnetic field. Okay. Later on, my collaborator at Zurich, Brad Nelson, was able to fabricate much simpler micro-sized swimmers. For example, this two-link swimmer, there is a nickel head. Nickel is ferromagnetic, and this semi-flexible polypyrrole. And there is a short flexible hinge here that in the model, it was short enough that we molded it like a pointed torsion spring. And you apply similar magnetic field, constant in the X direction, small oscillations in the Y direction. The torque acting on any magnetized link looks like this: cross product between magnetic field and magnetization vector, which is proportional to minus sine gamma. Gamma, you can see here, gamma is the relative angle between direction of the magnetic field and direction of the magnetized link, which means that the torque is actually acting to align the link with the magnetic field like a compass needle. But this magnetic field is rotating. It's not constant direction. That's why the swimmer is swimming. So we were able again to do all the boring stuff and perturbation expansion to get fancy expressions for the speed and for the energy. And we're able to find the dependence on parameters. Now we have additional timescales in the system. So we can find not only optimal frequency, we can find optimal non-dimensional stiffness of the joint. And we can also find, if we allow the two links to be magnetized, we can also find the optimal ratio of magnetization. Okay, once we did this, we wondered if we can explain the question about why the Dreyfus swimmer was moving in Y direction out of the blue. So the thing is that in the Dreyfus, there was a difference. The links were not ferromagnetic like nickel, they were beads which are super paramagnetic. Okay, so I'm not expert in magnetism, but we decided to assume that it's a two-link swimmer, simpler swimmer, but now the head is super paramagnetic. Even though I'm not expert in magnetism, I read the literature and I know that the torque has a different expression. The torque acting on the link, it's more complicated expression, but in bottom line, it is quadratic in the intensity of the magnetic field, but it is proportional to minus sine 2 gamma, double times the relative angle. And this starts to give some explanation because now, suppose that the magnetic field is fixed in a given direction, maybe in the x direction. What are the equilibria? The equilibria are zero torque, so sine 2 gamma equals 0. It has 4 solutions in the circle. It has 0 and pi, solution in which the link is aligned with the magnetic field and anti-aligned with the magnetic field. And it has the plus minus 90 degrees, it also sine 2 gamma equals 0. So also the perpendicular, we have other solutions. We have the x and the y orientations. Now we wrote the equations. The equations are just for 2 angles, phi and theta. Phi is the relative angle of the joint. Theta is the orientation angle of the head link. And these are the equations after identifying the time scales, nonlinear, time varying, time periodic system. And if we set beta to be 0, which means that there is no actuation, that there is static magnetic field in the x direction, then it becomes time invariant system, and it's easy to find, even though it's nonlinear, it's easy to find the equilibrium states. So we have phi in equilibrium is 0, and theta can be again 0, pi, plus minus half pi. But now we can actually analyze linear stability, right? Linearization. Familiar with this? Linearization, linear stability. So we can find that the aligned and anti-aligned are stable, and the perpendicular ones are unstable. This is statically unstable. But when we start to oscillate the magnetic field, it turns out that what happens is that there is a change in stability. So something which was statically unstable, periodic solution about the same equilibrium can be sometimes stabilized. Does this ring any bell to somebody? Something with a pendulum? Which pendulum? All right, okay. Let's see. So one thing that we did, first asymptotic limit, I will continue until the end of part 2. Is that okay? It's like 3 slides or 2. I will neglect part 3 because I'm running late, not only because of the protest, because of myself, okay? Because I'm too slow. Maybe I'm enjoying too much. Okay, so one thing we did is a limit in which it is fast frequency of actuation and soft spring, which means that the time scale of the viscoelastic time, response time is very long. In that case, we can actually do multiple scales. We can average over the fast dynamics of the input frequency. And this is actually the slow dynamic evolution of the averaged over frequency, over omega. This is theta bar and phi bar. And the thing is, after averaging, we have a time invariant system, non-linear system, but we can find equilibria and analyze their stability using linear stability, just like before. And you can see that this fellow suddenly appears, beta square minus 2. Once we do, and its sign is actually really important. So when we do this, we can discover, after some very simple math, that the configurations with theta equals 0 and pi, which means moving in x direction, are stable if and only if this amplitude ratio beta is less than square root of 2. And the y direction, the plus minus 90 degree, they are stable if and only if beta is greater than square root of 2. So either we are in this regime or in that regime. But this is not exactly what we saw in other simulations. So of course, it agrees with the previous observations of Dreyfus, but we weren't fully happy because we simulated the system and we also later did experiments. We knew that there is also influence of the frequency. And this square root of 2 is not a golden number. It shouldn't be the only critical value. So then we considered another limit. And in this limit is fast and stiff, very short viscoelastic time, and very fast actuation. In that case, mathematically, we could eliminate the equation for the angle phi and plug it into the equation for theta. And then we have a second order equation for theta. After arrangement, it looks like a mechanical equation, even though there is no inertia in the system. It looks like a second order equation with linear damping, but it's multiplied by a time periodic coefficient. And the stiffness term is also with time varying, and we have external periodic. So this reminiscent of Kapitza pendulum. So if you don't know Kapitza pendulum, let this movie be the only thing you can take home from this, and later you can do Google and YouTube and study about it. A wonderful analytical dynamics problem. So pendulum is something which has two equilibrium points: the down equilibrium point, which is stable, and the upward equilibrium point, which is usually unstable. If I'm perturbing, trying to put this on the head, it will fall. Okay. What happens when you start to oscillate, vibrate the base vertically in high frequency? The upward equilibrium can be stabilized for sufficiently large high frequencies. This is the movie. It will be recorded, and you can just do it in YouTube. So now when the base is vibrating, the statically unstable upward equilibrium becomes stable. So our equation is more complicated than the Kapitza pendulum. It's, I think, 3 times longer. So we had to do a lot of math in order to find the stability conditions and asymptotics. And I'm skipping all the math here. But then we found that the conditions for stability depend on both frequency and amplitude. And we have regions in which both solutions of X and Y are theoretically stable, bistability, multi-stability. And then I collaborated, I don't know to build microswimmers. I collaborated with a group from Chinese University of Hong Kong. They built the swimmer. The swimmer is like, it's not millimeter, it's 25 micron. It's actually less than this, with a super paramagnetic head. And the coil setup for magnetic actuation, and also the microscope in order to view the results and take measurements. This is from the microscope. First experiment, small amplitude, sweep on the frequencies. For small amplitude sweep on the frequencies, all the motion are in X direction. And there is optimal frequencies that maximizes swimming speed, just like Dreyfus with all the beads. When we increase what we did now in order to demonstrate the dependence also on omega, we increased beta, kept it constant, and start to sweep the frequencies. When they did that, there is this flip, the expected flip. So when beta is constant, something which is not square root of 2, we increase omega, and there is a critical omega for this 90-degree flip, like Kapitza-like transition in the stability. And this is nice. There is only one slide left on the microswimmers, which is, even in Purcell, the old paper, there was another mode of locomotion. This is just comparison between our model and the experiments. Sorry, this one I meant. Okay, there is another mode of locomotion, which is corkscrew. Which creature is doing this? This is very famous model organism. This is the E. coli bacteria. Okay, very famous, mentioned in Purcell paper, mentioned by very famous Howard Berg book. And after some decades, people were able to fabricate these corkscrew micro swimmers. It's like 50 micron long, and it has a very small micro size helix attached to a nickel head. And magnetic field now was rotating in the plane XY. Ignore the H. The H can be made also 0. So it has only rotation in the XY, that's enough. And this swimmer is just screwing its way through the viscous fluid. The downside of this is that it's very hard to fabricate this helical structure. It was, maybe now it's easier, but it was very difficult. And then we found out with our ATH collaborator that you can do it also with the same tooling swimmer. You take the same tooling swimmer with a flexible hinge and put it under a rotating magnetic field, rotating in XY plane. And it has very interesting dynamics. It was reported in one experimental paper and one only theoretical. And here is the interesting frequency dependence. For low frequencies of the rotation of the magnetic field in plane XY, the swimmer just stays in XY, just follows some phase shift from the magnetic field, but doesn't go in the Z direction at all. No swimming. After some critical frequency, this planar solution loses its stability and bifurcates into a solution that goes out of plane and starts to move in the Z direction, and the trajectory of the points of the swimmer are actually helical. After a while, we have an optimal frequency for maximizing the speed. And after more, we have a step-out frequency, which is when we lose synchronization between magnetic field rotation and the swimmer rotation. The phase shift is not constant in steady state. And I think, only one click. So in a paper which is now in archive, we were able to analyze this and get analytical nice results. This is the master of Tzvi, the joint PhD student for Shai and me. When he was doing PhD, he did something about micro swimmers. Two-link swimmer, it looks simple, but it's more complicated because it's now in 3D. So we need not only single angle theta and phi, we have spatial angles, we have Euler angles for description of just the spatial kinematics of the head orientation. So we have some theta, psi, phi, delta. So we have 4 angles, including the joints. I think I will have to stop here because soft robotics, the time is still rigid and not soft. So at some point there is a hard constraint, non-holonomic constraints on the timing. Is it holonomic maybe? Okay. So now, first of all, I know I'm late. Nominally, I'm very late. So if you want to leave, you can leave. And those who wish, maybe we can take a few minutes to questions. And those who wish to really ask deep questions, you can stay. But let's set your PhD. Okay.